Hello, this is Dr. Glassbrenner from George Mason University, and in this video, we will introduce the different parts of the Reproducible Research Toolkit that we will use during the semester. Having provided a motivation for why we would want to continue to improve the state of reproducibility in science, we now need to address the more practical question. For our purposes, what does it mean for a data analysis to be reproducible? Let's address this by listing a series of near-term and long-term goals. For our near-term goals, we will consider a data analysis to be reproducible if we can answer the following questions. Are the tables and figures reproducible from the code and data? Does the code actually do what you think it does? And, in addition to what was done, is it clear why it was done? E.g., how were parameter settings chosen? For our long-term goals, which may be goals you strive for after this class has ended, the reproducibility checklist should be extended to include these questions. Can the code be used for other data? And can you extend the code to do other things? How are we going to accomplish all this? That's where our course toolkit and working environment come in, which consists of several tools that are tightly integrated with each other and the course materials. Our primary tool will be R, which is a programming language. You can see a simple snippet of R code over here on the left, and the output from executing this code on the right. If you have never programmed before, that's okay. This course does not assume you have a programming background and takes things one step at a time. Part of the reason you will be able to learn to use R in a just-in-time fashion is because of the helpful tidyverse packages, which we can think of as a general-purpose utility belt for R that streamlines the language and provides us with a simple yet powerful set of commands for working with data. The traits that make tidyverse R accessible to beginners include its consistency, predictability, and readability. All of our work with R will be completed within RStudio Server, a full-featured editor that you can think of as our virtual workshop. RStudio sits on top of R and provides a convenient interface for handling the files and features we'll make use of during the course. RStudio Server is installed on our department server, and you will have full access to it during the semester. You will be able to access it at any computer, provided it has a modern web browser installed, such as Google Chrome or Mozilla Firefox. Don't be fooled by the fact it's a web app. RStudio Server is identical in functionality to the version you can install on your computer. We can't have a workshop without somewhere to store our projects and display our hard work. And for that we use GitHub, which is a platform used for sharing and collaborating on coding projects and, more recently, data science projects. GitHub allows us to save snapshots of our work to serve as a backup and can be used for group collaboration. A kind of classroom mode is activated for us as a class, which means everything is private by default, and I can distribute links that will, once you click them, give you templates to use in your homework assignments and projects. To become more familiar with R, let's go through a brief overview of its development history. The first stable version of R, version 1, was released on February 29, 2000. However, R's family tree extends back further, as R itself is an implementation of the S programming language, which was designed at Bell Laboratories in the mid-1970s. That means that some of R's idioms are over 40 years old. Base R, which is how people refer to a fresh installation of R without any extra packages installed, was built for statisticians and for doing data analysis, but not necessarily for modern data science. Its age and legacy brings along old implementations of data structures and abbreviated function names, which can be particularly confusing and strange-looking for beginners. That's changed in recent years. Over the last 3 years, the chief scientist at RStudio, Hadley Wickham, has led development efforts to bring R into the modern era with his tidyverse packages. What is the tidyverse? According to the tidyverse front page, it is an opinionated collection of R packages designed for data science. All packages share an underlying philosophy and common APIs. In practice, this meant reducing everything to a small core set of commands that all behave in a similar way, which is really nice for beginners. When you start using R, you will notice the code follows certain patterns. Here is a short list of the most common things you'll see many times while using R in this class. First up are what we call functions. Functions are named as if they are verbs, meaning they perform an action. The action is applied to the inputs you list inside of parentheses, as in the following examples. Here, we are saying to do this to this. So the function is acting on a quantity or object. There can be more than one input in a function. So we can do this to this, as well as to that, with those values we saved earlier. If that seems confusing, don't worry. It'll become more comfortable as you practice using it. A convenient feature of using R is being able to install packages with relative ease. We do this by using the install.packages function. So if we wanted to install the package of name package_name, we would type install.packages open parenthesis quotation mark package_name quotation mark close parenthesis. To use the package, you need to load it with the library function. Sticking with the package_name example, to load that package, you would run library open parenthesis package_name close parenthesis. Note that the packages are only loaded for your current R session. If you log out of or reset your RStudio server session, you will need to reload the libraries again. As for why we care about packages, it is because packages are how we bring in additional functions to use in R. A large amount of our work will take place in R Markdown documents. A short example of what an R Markdown file looks like is displayed on the upper portion of this slide. R Markdown files are the medium that will allow us to write a fully reproducible report. We can use these documents to generate reports with nice layouts by knitting the document. Yes, you heard that correctly, knitting. There's historical reasons for why it's called knitting, but we'll skip over that story. Each time you knit the document, your code and analysis is run from the top of the document all the way to the bottom. You will be able to format your text in your write-ups using a syntax called Markdown. With Markdown, simple combinations of symbols represent markups that you're familiar with from using Microsoft Word, such as boldface, italics, headers, bullet points, enumerated lists, and more. As for your code, that gets placed in chunks, which are defined by 3 backticks. Your narrative describing what you're doing, meaning your write-up, should always go outside the chunks. The benefit of this is if the document works for you and knits without error, then it should also work for me in the same way. By design, it requires you to write code blocks that can all run without error, which enforces code reproducibility. To wrap up, how exactly will we be using R Markdown files during the course? All your homework assignments, as well as the final group project, will be submitted for grading as an R Markdown document. Also, I will show you examples during the semester in a real-time demo format, where I will work through an example problem in an R Markdown document and describe what I'm doing out loud, and also by typing in annotations within the document. While you watch these, you should create your own R Markdown document and follow along. If this all sounds like a lot to learn how to do, it is for this reason you will be provided with template R Markdown documents to start with for each assignment. Over time, you will become more comfortable with writing in this format and making use of this workflow.